Okay, we are back in the lab. We are starting videos again. Kofi's getting upset because I don't have anything on the page. They're like, hey, you guys are already paying money and I don't have anything up on the page. They're like, Kofi's like, you better get something up here. We're going to take it down. Okay, we're going to make a video. We're going to start. So this is going to be the beginning of our Kofi adventures. We're going to deep dive into stuff a little bit more than YouTube, right? And then I'll kind of consolidate what's found and put it on YouTube. This will be less polished. You'll get a ton of extra information, and hopefully it ends up being cool. I mean, we'll see how it ends up working out. I think it'll be pretty cool. Okay, the first topic coming back is going to be PBX, polymer bonded explosives. This is going to be an interesting topic for a couple of reasons. Number one, it's the most requested topic out of anything by far. I've had more requests for PBX than any other topic since I started making videos. The other reason this is going to be interesting is because my polymer science background is non-existent. I don't have any training or specialty knowledge on polymer science in general. And so all this is going to be new to me. So hopefully it's new to you too, and we can go on the journey together. Now, what I do have is a lot of experience with government C4. I probably detonated several hundred pounds of C4 over the years, government manufactured C4 for the U.S. Army. So I've got a lot of muscle memory on that material, and any composition that is kind of found here that works, it'll be able to be compared and contrasted to government C4. Of course, my angle in all of this is that I always want to try to approach the topics to make them as readily accessible as possible. A lot of the materials that are used in explosive industry and munitions manufacturing, they're just not going to be available. So we're going to try to get as close as we can to things that are OTC, available over the counter, things that you can order. Maybe you can't get them in like Walmart or something, but maybe some stuff that you can order on the internet or that's readily accessible. That's the goal here. But the first step is just to kind of understand the nature and behavior of these polymer binders, what will be realistic to be able to be used and what is not realistic at all. And the only way to do that is just to do some testing. So that's the first step. I've got a control here, that'll be PIB. I've got a sample of polyisobutylene, that's the polymer binder that's used in C4. So hopefully we can get close to the consistency of actual C4 using that and using the government formulation. And we'll see how close it is. And that'll act as the control. But then we have some other polymers here. So I've got a Catchmaster bulk glue. This would be rat trap glue that's in a bulk can. And this is probably the most affordable source of it. It's tough to say what the material is because it's a proprietary secret. So you can't find on the MSDS, you're not going to find, what is exactly going on in here. But it's most likely polyisobutylene, and there might be some polybutene inside of this formulation. Don't really know. It typically works pretty well. It is pretty sticky and squishy, and so depending on how you process it, it's going to affect how much solid fill loading you can use, but it's a really interesting alternative to the practically unavailable solid PIB source. The other polymer that I want to test today is EVA, that's ethylene vinyl acetate. That would be like your hot glue sticks. This polymer is readily available. On some research, I discovered that there are some British formulations like from Rowan-X. They've got a couple of different, they're harder, more stiff PBXs, so for munitions loading, not necessarily for hand use. So they're not going to be as flexible as C4, but we may be able to play with that using plasticizers and see if we can get it moldable similar to C4. And if not, it'll just be a rigid PBX. But this is a readily available polymer, and so I want to use this. The other one that I want to check will be polystyrene, which is your styrofoam. Styrofoam's everywhere. It's probably the easiest accessible polymer that you can get. So moving on to solvents, I have we're testing right now, but apparently, from my findings so far, toluene is going to be applicable to everything. So toluene, non-polar solvent, it's going to work really well on PIB. It's going to work, probably going to work well on EVA. We'll test that today. I tested it last night on the Catchmaster glue, which is PIB or PB, and it's definitely effective on that. You can get a totally dissolved liquid mixture using toluene. So that solvent will be used across the board here. So in terms of an overview, just to kind of wrap your head around this, in the polymer science of polymer bonded explosives, you basically have your filler material, that's your explosive. You have your binder, which is going to be a plastic, and then you have some type of plasticizer, and then sometimes you have a processing agent like an oil or something like that. Most of this is going to depend on the polarity of the explosive material that you're using and the plastic in the plasticizer. So for instance, something like PIB, it's a non-polar hydrocarbon plastic. You're going to use non-polar solvents. So typically, classically, what's used with PIB, you'll see a lot of people recommending hexane or heptane. And sometimes you can even get away with, crude, gasoline or something like that. White gas works pretty well, which is going to contain those as fractions. But toluene is not typically associated with it, at least not in amateur energetics. If we were using a polymer that was highly polar, something like nitrocellulose is, and I'm not talking about the gunpowder, I'm talking about, actual nitrocellulose made from cellulose that's nitrated to high nitrogen content, 13%, something like that. It's highly polar. So you have to use a highly polar plasticizer. Well, that's where you get into other liquid nitrate esters. So nitroglycerin, propylene glycol dinitrate, diethylene glycol dinitrate. These are all really popular with that. Nitroglycerin, it's a little bit volatile. It gases off. And so you get migration of the mixture changing over time, and it can change the properties. But something that's really stable is like diethylene glycol dinitrate. So I ordered some of that. I've ordered, all these materials are all bought from, these are all purchased from donations from the old Patreon account that they closed down. So if you help me out on that, I appreciate that. Your support went into this stuff to, buy all this crap. But anyway, in terms of the materials we're using here, we got the several various polymers. We've got the solvent, which should be applicable to all of them, toluene. And then we've got mineral oil, which would be used as a processing agent if need be, and then dioctyl adipate. So dioctyl adipate is it's a plasticizer that you can find it on the internet. It is a little bit more unusual of a chemical, but it's kind of the key to really getting a fine PBX that's flexible and moldable, is disrupting the molecular interaction of the polymer using the dioctyl adipate. They call it, DOA for short. So the DOA should be applicable and compatible with all of these polymers, which makes, it makes the testing a little bit simpler because you can kind of compare and contrast the differences in how these materials behave with this solvent and this plasticizer. Now, just in initial experimentation, the conclusion that I came to immediately is that, you can go through a lot of high explosive material as the filler, just trying to do validation tests, just testing these combinations, playing with this material. You're just going to burn through high explosives. So we need to find a suitable substitute. The testing materials, make them inert to see how close we can get. And the most appropriate materials that I found so far are going to be confectioner sugar. Sugar is hygroscopic, so it's not ideal, but it should be able to give you, it's a really cheap material that should be able to give you an approximation of what the PBX will behave like physically when you go to actually load it with interject materials. The other one that I'm using is going to be a sample of melamine powder. So I've got some melamine. It's going to be inert. For this purpose, the density on this is 1.57 grams per cubic centimeter. So it's a little bit lower than, your more dense high explosives, like if you were filling with, pretty much any of them, PETN, RDX or HMX. They're going to be higher density than this, but this is close enough to give you an approximation, and it's not going to interact with any of these materials at all, and it's a kind of an inert non-reactive powder, so non-hygroscopic. It'll work really well. We'll try both of them and just kind of see what the difference is in their behavior. So the first step is going to be checking the solvent of toluene and seeing if this is going to be compatible across the board to at least a suitable level of performance for all of these materials. I think it should be. I've already tested Catchmaster last night. We need to test PIB, ethylene vinyl acetate, and polystyrene. Okay, so let's test some of this EVA. We'll try to dissolve just like a modest amount here. Let's see what we get. Okay, we've got about 4.9 grams of EVA. That's good enough for government work. Okay, now we're going to meter in some toluene. Ideally, you want to use the minimal amount, but we'll just way out of mass here. It's getting pretty translucent around the edges. You can see kind of it used to be a homogeneous color. Now it's getting, it's opaque in the middle. It's more translucent around the edges. Make sure that you have ventilation going because toluene is, it's toxic and it's also off gases a lot. It's poisonous. So make sure you're using ventilation. Okay, it appears that toluene is extremely aggressive because this has absorbed all of it out of 2 grams. So I guess we're going to go a higher quantity. Okay, so we've now got 5 grams of EVA, and we've got 10 grams of toluene solvent, and we're going to go ahead and put this on, stirring and warm it gently. So the temperature this is mixing at currently is 68 C. We're totally dissolved now. In the meantime, I've got a calculation over here. We're going to attempt an emulation of a Rowanex EVA-based PBX. So we're going to do 6% EVA, we're going to do 6% of the octyl adipate, and we're going to do an 88% filler. Okay, we are ready to begin attempting to add solid filler. So I opted to use sugar, confectionery sucrose, instead of using melamine, reason being that I think we're going to have some difficulty with this mix, and just to be safe, I want to make sure that we're not totally wasting melamine because it's a little bit more expensive. Sugar's cheap, we'll try that. We'll just see how this starts mixing in. Of course, it's obviously going to get totally out of control on viscosity and get really thick quickly, and we're going to have to pull this off and hand process it, and it is thickening up quite a bit. Lots of fumes. Make sure that you guys are using ventilation. I've got doors open in here. Actually, not as bad as I thought. It's thickening up. Okay, we're going to have to lay this out and start hand kneading it. Okay, I've been hand mixing this for a couple of minutes now. Let's talk about this. So this is the consistency here. This is crumbly. Okay, this is at a 6%. This is at 6%. Polymer, EVA polymer, and 6% plasticizer. And this is just, if you squeeze it, it's going to consolidate and then it just crumbly. So what that typically means is that your polymer load is too low. So if it's crumbly, that means you got too much filler, not enough polymer. If it's too squishy and doesn't really hold form, it's not firm, then that would be a sign that you need additional filler usually. But this is a sign of too much filler. So the proportions of the Rowanex, 88% fill with 6% binder and 6% plasticizer. It's not looking good, at least for sucrose. And I kind of imagined it was going to be like that. So I guess the next step on that is going to be to record that proportion doesn't work, and then attempt something else with a higher proportion of EVA.